going to talk about this afternoon is Java on CRaC. I think the marketing department might need to have a bit of a think about that as a name, because it might not work too well when we release it. But we'll explain exactly what CRaC means in a minute. So I'm going to do the first part of the presentation. I'm going to talk about what it is that CRaC is and how it relates to Java. And then I'm joined by my colleague Gerrit down here, who will be giving us a demo at the end of this actually in action. So let's get started then. So the first thing that we need to talk about is, just to set the scene, why is Java so popular? And there are obviously a number of ways that you can answer this question. There are a number of reasons why Java is a very popular language. It's always in the top 3 of the surveys that show, which is the most popular programming language that people use. And the reasons for that are that it's a great language. We like Java because not only is it easy to write, it is easy to read. And that's really the kind of important thing. It's easy to read as a language, so you can maintain your code. Another reason why Java is so popular is because we have lots of libraries. And pretty much anything you can think of, you can find a Java library that will help you achieve that task. And almost all the time, you can find a free open source version as well as a commercial one if you want it. So having libraries is great because it means we don't have to write as much code. And then, of course, it has a great community. The fact that we're at this event here, focused on developers, it's focused a lot on Java. There's other things as well, but there are many conferences that focus purely on Java. There's Java Champions. Who's a Java Champion? Oh, look at this. That's great. We've got several Java Champions there. We've got the Java user groups. Again, the Atlanta Jug is helping to organize this. And the other thing, of course, is it's easy to find Java programmers. All you have to do is say, I need a Java programmer, and somebody will step up and say, I can program in Java. But ultimately, I think the reason why Java is so popular is not all of those 3 things. The reason that Java is so popular is because of the JVM. And the JVM is really, as it's been described, the jewel in the crown. We'll get it out in a minute. What does Java Virtual Machine do for us? Well, it gives us the ability to have write once, run anywhere. The thing that's been in Java right from the very beginning. You can take the same compiled code and move it to whichever platform you want. As long as you've got a JVM, then you don't have to recompile, you don't have to do anything to your code. That's great. It also has excellent backwards compatibility. I've actually taken applications compiled on JDK 1.2 and run them on JDK 17 without recompiling them. It works, there's nothing to do that. I also found I had some applets that were written on and compiled on JDK 1.0, but applets are no longer supported on JDK 17, so I couldn't actually run them, which is rather frustrating because it would have been really nice to see something on JDK 1.0 actually running on JDK 17. And then, of course, the real power is the fact that it gives you a managed runtime environment. That means that from the point of view of memory management, you don't have to do anything. You simply say, I want a new instance of string, and the JVM will figure out where to put that in the heap. When you don't need that string anymore, JVM will garbage collect it automatically. You don't have to worry about freeing up space and things like that. So these are all good reasons why Java is so popular. But there's a thing that we face with Java, and it's the cost, if you like, of having this ability to move applications around without having to compile them for a specific platform. Class files contain bytecodes. We know about that. And those are instructions for a virtual machine, hence JVM, Java Virtual Machine. What that means is obviously they're not the instructions of the specific machine that we're running the application on. So what we have to do is convert them from bytecodes into whatever instructions we need for the platform. And the way we do that changes over time. Initially, when you load a class and you start running a method, it's going to be interpreted. And interpreted is where we take each bytecode in that method and we convert that to a set of native instructions which can be executed on the processor, maybe system calls, whatever's required to make that bytecode work. But there's no optimization of that at all. Literally, we take every bytecode in sequence and we execute whatever native instructions are required, even if we're doing the same thing again and again and again. The only time when that actually, there's a little bit of optimization where you sometimes get pairs of bytecodes which can also be converted into a set of instructions. But it's very inefficient from the point of view of getting better performance. What then happens, and what happened from really JDK 1.2, was the idea of adaptive compilation. Adaptive compilation says, okay, let's start running in interpretive mode, but now let's keep count of how many times we call each method. When a method gets to a certain threshold, we say that that is a hotspot of code, hence the name of the JVM. Having determined that's a hotspot, we then pass it to a compiler and say, take that whole method, compile it into native instructions, and do that in such a way that we can understand that this is a set of instructions and we can optimize at least somewhat based on that code. That happens using two compilers in the hotspot JVM. So there's C1 and C2. Pretty novel naming. C1 is a compiler which is designed to compile code very quickly. What we want to do is we want to get that code to be able to use it as quickly as possible. We run that code for each time the method is called until we get to another threshold. But at the same time, we also collect information, profiling information, so that we know how that method is being used. When we get to the second threshold, so this is one that's really being used a lot, then we pass the same method to the C2 compiler, which uses the profiling information to then say, okay, let's recompile it, but let's apply lots more optimizations to get better performance from that method. Now, the problem with this is that there is no, if you like, temporal state associated with this. When you start up a JVM with a set of class files, it does that as if it's never done it before, because, well, probably hasn't. So it starts up and it goes through this interpretive mode, identifies hotspot methods, compiles them with C1, profiles them, recompiles them with C2. That's great. If you restart the same application without recompiling it and making any changes, the JVM will do exactly the same thing again. It will go through that interpretive mode, it will profile things, it will identify hotspots. There's no memory between different runs of the application. So what this leads to is, if we look at the performance of the application, and we're not looking at the performance of the application code, what we're looking at is the performance of the application in terms of the JVM, if you like. So we start off here with low performance because we're doing interpretive mode. So that's the slowest way of doing things. The yellow bit of code at the left-hand side of the graph there. Then we get into the green part of the graph, which is where we're running C1 compiled code. Runs a bit faster, but it isn't really that much better than we get with interpretive mode. The real benefit comes when we get our C2 compiled code and we gradually get all the frequently used methods compiled with that. And we will at some point reach a steady state where everything that we're using regularly is compiled and it's optimized as much as we can. But we'll also see, as we warm up, we'll get some dips in performance. And those are due to what are called de-optimizations. And I'll kind of come back to that in a minute because that's quite important. So the net effect of this is that we have warm-up time. And for an application, that could be, a few seconds, if you're very lucky, or it could be a few minutes. In the case of this particular graph here, which we generated from, some random application that we ran, that took about an hour to get to the optimum level of performance. That's fine if you're going to run the application for days or weeks. But if you're in a microservices architecture where you want to be able to spin up instances of a service to adapt to changing loads in a very dynamic way, then waiting an hour for your microservice to come up to full speed is really not going to be the best way to run a microservice. So what we need is a different way of doing this. If we look at running our application several times in a row, As I said, there's no memory across runs of an application. So we run our application, we go through this warm-up phase, we do all of our analysis. When we run it a second time, we do exactly the same thing. So the graph looks exactly the same. We have to go through all that process of warming up and doing things. And then we do it a third time, same thing. And the other downside of this is also that by doing all this compilation as the system warms up, we're taking resources from the application itself. If we're running in a container that only has 2 vcores, and we're going to use one of those vcores to do all this compilation, we've immediately halved the amount of processing power available to our application. During warm-up, not only do we get slower code because it's not optimized, we also get much slower application performance because we're using the processor to do the compilation. So this is all downside. What we really want is a different profile. What we'd like to do is say, okay, let's run the application, get it warmed up, get it to a steady state, and then the next time we run it, let's just start off from where we were and continue with the same level of performance and continue. And if we want to do it a third time, we get the same thing. So this is all good. This is what we really want. Warm up once, and then even though we've stopped the application, we should get the same thing. Now, what people will often say is, well, rather than using bytecodes, isn't the solution just going to be, let's compile it using ahead of time compilation? Because that way, what we're doing is, rather than creating class files with bytecodes in them, let's create a native executable which we can run on our platform. Okay, we lose the write once run anywhere side of things, but at least we can get very fast startup. We can immediately run with fully compiled code. So that is an approach, yes. It's good because we don't have to interpret bytecodes. We don't get this low level of performance when we start up. We don't have to analyze all of the code. So we're running native instructions straight away. There's no looking for these hot methods that we need to compile. And there's no runtime compilation of our code. We don't place a load on the CPUs. We don't degrade the throughput of our application in order to do the compilation. Great, this is all looking good. And we start at full speed straight away. Wonderful. And there is a solution that does exactly this. If you've looked at GraalVM, they have the idea of native images. And that essentially takes Java code and many other languages, creates a native executable for that, and allows you to run very, very quickly with a much smaller footprint. So it's a great idea. Okay, so the problem's solved, right? So let's see, we've been talking for like 15 minutes, that's it, game over. Except it's not. Not so fast. And this is the problem, you see, because if we look at what happens with Java, we need to look in a bit more detail about how things work. AOT is by definition static. We have statically compiled code. And the code is compiled before the application is run. So we have no idea of what's going to happen when we run that code. The compiler doesn't know anything about what happens when you execute the application. It can see the methods that are being used, it can see the instructions that are being used, but it doesn't know how those are going to flow. So it's got no knowledge of how the code actually runs. People have provided solutions to this. There is a thing called profile-guided optimization. It's been around for a very, very long time, really since the beginning of high-level compilers almost. And what that says is, okay, compile your code statically and then run it, but profile what's happening when you run your application. The idea being that you run it with a representative load, you take information about how the code works, which paths are used frequently and so on, and then you feed that back into the compiler, recompile it again, so that you can optimize it in the best way for that profile. So that's good. That will give you better performance. But it only helps partially. What we find with JIT compilation is that we can do a thing called speculative optimisations. And I'll give you a couple of examples of how this works. First example is we can inline monomorphic sites. What do I mean by that? I create a class called animal, and within the animal, I'm going to encapsulate some data, which is the color of that animal. And I need an accessor method so that I can return the color. Great, very simple data type. If I use that, obviously I'm going to say my color equals animal.getColor. The drawback to that is obviously I'm calling a method, and in order to call a method, I have to pop a frame onto the stack. I have to execute the code within the method, which is simply to return the value of the variable, and then I pop the frame off the stack. And that's a lot of work just to get access to one value. The compiler will look at that and say, I can inline that and effectively say, rather than calling the method every time, I'll simply take that private access variable and turn it into a public access variable, but only where I'm using this method. So I'm not breaking the contract with the compiler. I'm simply saying that in this case, I can inline that because I know exactly what's going to happen every time I call that method. That works so long as we only have one implementation of getColor. And so if you subclass things, if you have a overloading of methods, then there could be a method that gets called which doesn't just return the color, it does some other processing as well. And in that case, you can't then simply inline it. Another example of speculative optimizations is branch analysis. And so it's a slightly convoluted example here, but it's good to show you how these things work. What we can do is, in this method, we're computing a magnitude, whatever that is, and we pass in a value. And then we've got a conditional statement which says if the value is greater than 9, we're going to calculate what the bias is that we want to use here by calling a method with the value. If the value is not greater than 9, we simply set the bias to be 1. And then we're going to return math log base 10 of the bias plus 99. When we run our application code and we do the interpretive mode and the C1 profile mode, we can count how many times the application code goes through each branch of the conditional statement. When we come to compile it, if we see that we have never gone through the true branch of that if statement, then the compiler can compile based on that information. It can speculate that the fact that we haven't gone through the true branch up until this point will continue in the future, and we're never going to go through the true branch of that statement. By doing that, we can then change the code internally. So we can say, okay, rather than doing all that code we had before, we'll simply say, if the value is greater than 9, then we'll call uncommon trap. And that says the optimization that we applied here, the speculative thing that we said, is actually no longer true. So we have to be able to deal with that situation because obviously the contract with the compiler says that we have to be able to deal with that. But if it doesn't, and so the speculation that we're not going to have a value greater than 9, we can then reduce the code that we had from calling the log base 10 method on math, calculating 1 plus 99 every time. We can simply reduce that into return 2. So that's much better code than we had before. But it will only work if the value remains such that it's not greater than 9. So these are speculative optimizations. And what we found at Azul is that speculative optimizations really generate over 50% of the performance enhancements that we get with JIT compilation. They're really, really important to getting good performance for Java applications. However, what we don't want is this de-optimization. And that's the thing that I mentioned on the graph that I showed you earlier. De-optimizations are where we have a situation where we've optimized based on the information we had, but then something changes and that speculation turns out to be false. So suddenly we have value is greater than 9, or we have a class loaded, which means we now have a different implementation of getColor. So at that point, we have to throw away the code that we've compiled and then potentially recompile it again. So de-optimization is really bad for performance. Firstly, you're throwing away code that you've already compiled, which means you've wasted resources with the CPU, and then you've got to recompile it, so you've got to place a load on the CPU again, and then generate new code for that. Plus, you've got to fall back to interpretive mode, or maybe you've got C1 cache code, you can do that as well. So if we just sort of summarize the AOT versus JIT discussion, AOT has advantages, but it also has a number of disadvantages for performance. So one is that with the head time compilation, you can't do as aggressive method inlining as you can with JIT compilation. This is one of the most common techniques for improving performance on compiled code by saying, okay, let's take the code of a method and simply inline it into the loop or whatever you've got to get better performance. But you can't do that if you don't know whether there's going to be some class loading at runtime. AOT can't have runtime generation of bytecodes. There are certain pieces of code that do that to generate code as the application runs. Can't do that. Reflection with AOT is very complicated. If you look at the way Grunwald deals with reflection, then you have to do a lot of fiddly stuff to actually make that work, if you can, in fact, make that work. The other thing, obviously, you can't use speculative optimisations. You can't have code that's compiled and then be able to recompile it at runtime. And so overall, the performance of AOT code is typically going to be lower than JIT compiled code. Of course, the advantages are you get full speed from the start and you don't get the overhead in terms of the CPU, reducing the performance of your application throughput. On the JIT side, yes, you can use aggressive method inlining because wherever you do that method inlining, you know exactly which method is being used, which classes are loaded. If class loading happens at a later point, you can invalidate that method and then recompile it. You can use runtime bytecode generation because you can do that during running the application. Reflection is, I say, relatively simple because reflection is never really simple. You can use speculative optimisations, and overall, typically, the performance will be higher. Not always, but it will be typically higher. But the downside is it requires this warm-up and it requires the CPU overhead to compile your code. So coming back to our graph, if we look at JIT compiled code, this is the graph we're going to see. We get up to our optimum level. Compare that with ahead of time compiled code, and we're going to see something like this. So yes, it starts up faster, but the level that you're going to get to overall is going to be lower than with your JIT compiled code. So you kind of lose on one side but gain on the other. Even if you use profile-guided optimization, what you're going to see is, yes, that will bring it up slightly, but it's not going to bring it up to the same level that you get with fully JIT compiled code. So what about a different approach? And this is where we're going to get into the idea of the CRaC part. In Linux, there is a thing called coordinated resume in Userspace, or as we like to try and refer to it, CRIU. It's not an easy word to pronounce because it doesn't really have quite the right letters in it, but we call it CRIU. It's a Linux project, and the basic idea is to say you have a running application. What you want to be able to do is freeze that application such that you can take a snapshot of it, all of its state, and then at some time later, you can restart it from that saved state. And the idea, like I've drawn here, this is an example sort of diagram, is if you think of like the basic von Neumann machine. Von Neumann machine says you've got input, you've got output, and then you've got something which has state saved in it. So you've got memory, you've got registers, and so on. If we can take a snapshot of all of that state, then we can simply replicate it at any point we want, and we can then start running from there. Because there's absolutely nothing in that information which would prevent us from doing that. As long as we've got the program counter at the same point, the values in the registers are the same, the information in the memory is the same, then everything will just work, kind of, within some limitations. We'll talk about what those limitations are. Technically, you could also move it to a different machine. So as long as the architecture is the same, you've got the same instruction set that you could use, you've got the same amount of memory, then you can simply take your snapshot, move it to a different machine, and it will be able to start up on that. So what we thought was, okay, let's look at that and think about how we could use that for Java applications. So looking at CRIU, it's mainly implemented in Userspace, which is good because our JVM is an application that runs in Userspace. There are a couple of little things that are necessary within the Linux kernel, but they've been around for quite a long time. So they've been in there since the 3.11 kernels. That's, I don't know, many years ago. What they originally designed this for was migration of containers. And so if you look at things like Docker, and I'm sure Gerrit will mention this when he does his demo, they tend to use some of this CRIU stuff to actually enable you to take a container and then take a snapshot of it and then be able to use it again. It supports quite an extensive set of features. So you can take all the processes you've got. If you've got a process tree, you can take all the threads that you have. All of that will be recorded. Application memory, as you expect. Memory map files, shared memory, because of course this is at the operating system level, so all those things are available. It will support open files, it will support pipes, it will support FIFOs, and it will also support sockets, so all of the things you need in terms of the interaction. Intra-process communication channels, timers, signals, all of that is provided. And in fact, because of the complexities of some of this, they also provide ability to rebuild a TCP connection, but without having to exchange packets to say that. So you can do it from one side only. That's something which, when I look at that, it's like, that's pretty cool that you can actually do that from one side only. So you essentially rebuild the TCP stack based on the state that you had before, and you hope that the connection will work. Challenges in terms of the CRIU. So obviously, if you move your state to a different machine, then you've got to be very careful, because if you had open files on one machine, does the file exist on the machine you move it to? And if it does exist, is it going to be the same as the one on the machine you moved it from? So there's obviously issues in terms of state for open files. Shared memory, again, would be very difficult to replicate if you moved it from one machine to another, because if you're relying on inter-process communication through that, then other processes that are running expecting that to be available would be difficult to replicate on that side. Also, what about if you use the same state and try and restart multiple instances? That could get very confusing. Technically, you could do it, but it would get very confusing in terms of each of those instances is going to think they're the original, and suddenly they're multiple instances of the same thing, and that could sort of lead to sort of, I guess, sort of Linux schizophrenia type of thing. JVM, therefore your Java code, could assume, or would assume, that it's continuing its tasks, but it's very difficult to use that effectively if you just said, let's take the JVM and run CRIU on it and say, let's take a snapshot of a running JVM and then restart it again. So what we thought was, let's take it to the next level. Let's do it at the Java level rather than at the operating system level. The important thing, though, is to make the application aware that it is going to be snapshotted, and then also make it aware that it is being restarted. That allows it to take whatever action is necessary so that it can essentially tidy things up and then restart things necessary to the application before it starts executing code. So we've got our application running, and then what we say is, right, we're about to make a snapshot. So you need, as an application, to do certain things to tidy up and get ready for that snapshot. We create the snapshot, and then some point later, we decide we're going to restart that. So what we would do is we'd say, okay, call a method which says you're being woken up from a restore. What do you need to do to get things ready to have the application continue on what it was doing? And then it continues. So CRaC does impose more restrictions than CRIU. It says that you cannot have any open files, you cannot have any open sockets. And this to me makes a lot of sense, because if you're going to try and move these things around between machines, open files, open sockets are really difficult things to deal with. So let's just make sure that that's not possible. Now, obviously, by doing that, it means that when you are told that you're going to be snapshotted, you would then, in your code, say, right, let's close that file, let's close that socket connection. And then when you get restored, you go, right, now I need to check that file. Does the file exist? Is the size the same? You know, you could do certain maybe CRC checks or something like that on the file in order to determine that you've got the right information to continue the application from where it left off. And in fact, if you don't do that, you don't close things down correctly, then the checkpoint will be aborted if it finds that you've still got open files and so on. So how do we use CRaC API? So it's quite simple. In fact, it's a very simple API. What we do is we have the idea of a resource. And a resource is an interface that you implement in your class. Something that you're going to want to have state that's saved or needs to be told about a checkpoint. So you implement the resource interface, and then there are two methods that get called by the JVM. First one is very logically before checkpoint, where you close your files, and then after restore, which says open those files. So they're callback methods that are called by the CRaC system underneath, and you can take whatever action is required. How you use those is registering a resource. So you implement the interface with your class, and you say, now I've got a resource. You need to register that with a context so that it knows which classes need to receive the notifications. And then in order to get the context, we have a global context, which you can get, or you could implement your own if you really wanted to. But for now, really, everybody's going to use the global context. So the idea is that a resource will be registered with the context, and you get the context from the core, which is providing you the global context. Like I said, it's actually very simple. When you use that, obviously the global context maintains a list of resources. When we decide to do a checkpoint, all of the resources in that list will call the before checkpoint method on that in order to get the resources used in the way we want. And then when we do a restore, each of the things in the resource list will be called, will have the after resource method called, but in the reverse order. So this is important, you see. So if you think that you add the resources in the order that you think that you need to shut down certain things, when we restore it, we want to have that order reversed so that you're opening up things in the right order based on how you close things down. I hope that makes sense. So you've got one order for shutting things down, and then you reverse that to open them up again. As a simple example, how am I doing for time? Yeah, good. So a simple example, if we were going to run like Jetty. So we've got a simple server manager class, we've got a server, and then what we're going to do is simply create a server on port 8080, and we set a handler for that, and then we start the server. Okay, that's great. Simple piece of code. If we want to use CRaC with external initiation, then what we do is we use jcommand. So you basically send a command to the running process, and in this case we'll say jcommand target example jetty 1.0 snapshot.jar, and then we call jdk.checkpoint as the command that we want to execute. The JVM that we've modified in our proof of concept will understand that command, and it will say, right, where are the resources that are listed in the context, and then start calling the before checkpoint method on those. And we see that the command has executed successfully. Unfortunately, it didn't, and this is one of the things that I really think we need to change, because if you look at the log file, you'll actually see this, which says JDK CRaC implementation checkpoint open socket exception, because of course we didn't close the server. So we had a running server, and when we tried to do a checkpoint, the system said, oh no, you've got an open socket, if you like, and so we can't do a checkpoint on that, and it rejects it. So we shouldn't really say command executed successfully, because it didn't execute successfully. What we then do is we say, okay, to really make this work, we take our server manager and now we implement the resource interface, and that means that we add two new methods, which are the overridden versions of before checkpoint and after restore. And then you can see very simply in the before checkpoint, what we do is we say, take the server that we had and stop it running. And then when we get to the restore, we say, take the server we had and make it start again. So it's very logical, we stop it, do however long we want to freeze the application for, and then when we restart it, we start the server again. And if you run it again, that would then work. You can also use CRaC programmatically, meaning you can actually do a checkpoint restore from within your code. You don't have to do it through jcommand, you can do it internally in your code. That is just doing core.checkpoint restore, and that will then do the same thing for you. So we can throw a couple of exceptions if it doesn't work, but that's about all that. Right, how good is it? Does this actually work? So what we've done is to create a proof of concept. We took OpenJDK, and we implemented the sort of low-level CRaC functionality so that we could have core, we could have the ability to call that command, and then use CRIU underneath. So right now it only runs on Linux because we have CRIU that allows us to do that. Obviously on Windows and Mac, there are not equivalent technologies, but if there were, we could implement those. So these are the kind of results we got. What we did was we took some sample applications. So we did Spring Boot first, and we said, okay, run it on a machine, and how long did it take to get to first operation? So how long did it take us to get to the point where we could actually do a transaction? In the case of Spring Boot, it was 4 seconds to do that on whatever machine we were running. Using CRaC, essentially getting to the point where we've taken a checkpoint of that and then doing a restore, rather than taking 4 seconds to get to the first transaction, 38 milliseconds. That is 2 orders of magnitude faster, which is, to me, pretty impressive. Micronauts, again, there's another framework. In this case, it took us a second to get to first transaction, and we reduced that to 46 milliseconds. So again, sort of that's a good order of magnitude better, 2 orders of magnitude better. Quarkus, which sells itself as Superfast startup for Java applications, that took 980 milliseconds in the example that we were running, and when we did a checkpoint restore on that, 33 milliseconds. So we've got quite consistent results here in the sort of tens of milliseconds versus thousands of milliseconds. And XML transform, which probably isn't the best example, but that was, again, 4.5 seconds versus 53 milliseconds. So all very good results in that sense. The other thing we did was look at the sort of time to complete a certain number of operations. And the obvious thing here is that in terms of, by using CRaC, because we get the performance level that we had when we stopped running it, we can run at the same level again from there. So the red line shows we're using OpenJDK, and you'll see that there's a curve there, which is where it is doing its startup, it's doing the analysis and compiling code and so on, versus what we're doing here with the blue one is we straight into that performance level, and we get very linear results on that. So it takes less time to do the same work. Same thing with Quarkus. I'm not going to show you all the graphs for this, but these are just the 2 that I picked out. Quarkus, interesting because it shows a bigger differential between the 2 results in terms of the time taken to achieve a certain number of operations. So just to summarize this part before we go over to the demonstration. So CRaC is a way to pause a JVM-based application. It doesn't have to be Java code, it could be Scala code, it could be Kotlin code, just as long as it's bytecodes. What we can do is, as I said, take a checkpoint of a running application and do it in a controlled way. So the application is aware that it's going to be checkpointed, and then we can restore it at some point in the future. Potentially we could do that multiple times. We could actually run multiple instances of this if we wanted to. There are some restrictions on what we can do with that, but certainly looking at the way that you can write the code in the before checkpoint and after restore, you could write code that would take into account the fact that there could potentially be multiple instances you're running. Benefit, obviously, is extremely fast performance to full performance level. You get all the benefits of that JIT compile code, all the speculative optimizations, you've avoided all the de-optimizations, and get that right from the beginning, versus the ahead of time compile code where, yes, you get very fast startup, but overall the performance level is going to be lower. So it eliminates all of the things that we've seen in the past, the hotspot identification, the method compilation, recompilation, decompiles, and so on. Really important thing about this is it is now an OpenJDK project. We submitted it to OpenJDK, and the OpenJDK people said, yes, looks like an interesting idea. Red Hat are joining us on this. They're very interested in this, and then literally I was just talking to somebody from IBM earlier, and they're also interested in helping us with this project. So there's a lot of work going on. It's not quite finished yet. I wouldn't sort of say this is production ready, but it is certainly an interesting idea in terms of what we can work on. So there's a couple of links there for the wiki that we've got, where there's more information about this and some more graphs, and then there's also a GitHub repository that you can download the code from. So with that, I'm going to hand over to Gerrit, who's going to do the demo. Right. Oh, yeah. question?
When you restart the checkpoint, it comes with all internal caches, right?
That's a great question, and I'm going to let the demonstration speak for itself. So hold that question. If it's not answered after the demo, then...
All right. Can you hear me? Yes, you can. That's good. Perfect. Yeah.
That's the recording one.
So what we see, we have, I prepared a little example, so which is just, it's a Java code that it calls a loop every 5 seconds. And in this loop, we calculate prime numbers from 1 to 100,000 randomly picked. And each time the number is calculated, it will put into a cache. So that means the first time, cache is empty. It will take some time to get through all the numbers. And then second time faster because the cache is already filled a little bit, because the cache also has some timeout. After a couple of seconds, it just forgets the old values and cleans up again. So what we will see is something like first time it takes 30 seconds, second time it runs the loop 10 seconds, and it then goes down. So this should show the application warmup. And then we will create a snapshot or a checkpoint and then restart it. And then we will see that the direct start should be very fast at that moment in the area of milliseconds instead of 30 seconds, right? So let's give it a try. I just have 2 shell scripts. This code is available on GitHub. So if you would like to try it, you just come to me and ask me. I can give you the link to the GitHub. So it's nothing really secret. And in the shell scripts, I just call Java -jar with a specific parameter for the CRaC stuff, and then I just start the jar file, and in the checkpoint, I just call the J command stuff that we saw. So it's just to make it easier to start. So we start it up, and you will see the process ID here. So, and yeah, it's mentioned that it will take up to 30 seconds. This is because it's running on an external SSD in a virtual machine. So on my M1 Mac, it takes just 1.5 seconds to run. Here it takes 30. So, but it's good for the demo. And
slow is good.
Yeah. So yeah, you will have to wait. Like I said, first run, pretty slow. So the idea is, if you, and we will see that you see first run 27 seconds, something like that. Cache is 63% filled. That means the next time it runs to the 100,000 prime numbers, it's faster. So you see 10 seconds, and now it will really be faster and faster. So this is in principle the stuff that we see when we start up an application. Everything's caches will be filled up, and so on and so on. So, and then now it calls this method every 5 seconds. And it will, at some point, there are some de-optimizations, and then at some point it will settle around, whatever, 40 milliseconds or something. So we wait a little bit longer before we create the checkpoint. And then you see, okay, now we come down to 51 milliseconds, and the cache is more or less steady now. So now let's just create the checkpoint. And you see what it does on the left side. It just tells us that I have 2 resources here. It's the main class and the cache, and they have been shut down in this order. And when we restore it, it will restore it in the reverse order, like Simon mentioned, right? So, and we also see it tells you on the right side, it tells you the process ID here. So you see, okay, this is the process ID. That leads to the problem. You can imagine if I would like to start that a couple of times, Linux will be like, wait a minute. This process ID is already running. That doesn't really work. But just think about a Docker environment. There it's capsulated within the Docker container. So that means you can create a Docker container, warm it up, create a snapshot, and then you can use that container and just start it up multiple times, and it's already warmed up. But now let's see. The last run was 45 milliseconds. Cache was filled 100%. So let's restore it. And in the restore, what I do here, I just call Java, and then I call it with a specific command to restore, right? So this, if you see the code, then it's just one line, but it's easier to type this one. And you see directly 44 milliseconds, and 5 seconds later it will call it again. Yeah, see 37. The cache is already filled. So you might gonna ask yourself, how does it work? Because I talked about some timeout stuff. That means I stop the application for a couple of seconds. So when I started up, the cache should say, wait a minute, everything is outdated, and flush the cache. And it does. So what you have to do to avoid this stuff is before I shut down, or before I create the checkpoint, I just store the current epoch milliseconds in a variable, which will be then in the checkpoint, right? In the checkpointed file. And when I restore it, I just take the current milliseconds and then just the delta I add to all values in the cache, and then you are up and running again. And the interesting part is now I can just restore again, and we'll see again, because it restores from the same checkpoint at the same state. So, and this will also work with bigger applications. Like you said, we did that with Spring Boot, with Quarkus and all that. And I think it's quite fascinating to see. It just depends on your hardware, right? How fast can you load the code from your storage into the memory and restore all the resources that you use, like files, open, and connections and stuff. But this is really the whole startup time. And that's quite impressive. So, like I said, the code is not very complex. You can look it up on GitHub if you're interested. It only runs on Linux x64, I have to say that, and you need a specific version of the kernel. I think there are some versions that doesn't really work. We don't know why exactly. It depends on the CRIU version that comes with the kernel. But it's not so hard to figure out. So it's also documented, and if you have questions, you can always just let us know. Yes? It creates a set of files. For this demo, I think the files, it's 20 megabytes. That's the whole stuff here.
Yeah, because that's obviously going to depend on how much stuff you actually got in terms of state. So if you do like Hello World, it's not going to be very big. If you've got like a gigabyte of like storage.
On the right side, you see it. This is the files that have been created, right? So it's not that many. Oh, you would like to see the size? Oh, sorry. Here you see it's there you go. It's mainly, it's not all big files. There are some in there. Here you see this one, right? Yeah,
because there'll be one that has the cache in it, won't there?
Exactly. Yeah. So because we have the cache, the 100,000 numbers and all that, it has to go somewhere. So that's. Oh, as far as I know, it compacts the JVM before you do the checkpoint. This comes with the CRaC, and then you have to think about it like this. So when you call the CRaC before checkpoint, the JVM will put into a safe state, like compact everything and make sure that this is a very compacted, savable state, and then you restore from there. I tried that, but it didn't really work. And this is because at the moment it's really work in progress. So you can download the JDK. It's available if you look up the links. You can just install it and use it. So it's really like, that's what I did. And you can use whatever code. So I have a couple of demos that you can you can even run the Spring Boot demos, and they are also available for running. So if you don't believe us, you can just check it. Yeah, so that's it.
Oh, yeah. Another question? As far as I know, I would have to. Oh, the question was, how does native memory impact this? So if you're using native memory, then how would it? Yeah, I haven't tried that.
Me neither.
I suspect that, well, because it uses CRIU underneath, so it would depend on how CRIU would support that, which I believe it would. But yeah, I'd have to have a look at that. But
and it comes with CRIU, right? So no need to install it. The JDK version comes with the CRIU version. So that's also the reason you need a specific kernel because of that, because we deliver the CRIU. We would like to make it easy for people to use it, right? You don't want to have to, you need to install CRIU first and set it up, so that it comes with it and everything's there. But yeah, that's the current state. Like we said, it's not really there yet, but you can test it and play around with it, and it's impressive what you get for results out of that.
Yeah. I think we've been working on this for about a year now, maybe a bit longer than that, actually, maybe 18 months. I know we've had some ideas around this for quite a long time, but it's only recently that we've actually sort of got it to a point where we felt it was ready to at least submit to the OpenJDK so other people could play with it. Because you don't really want to have something that's just like half-baked idea. So we really wanted a full proof of concept that we could show that worked, and then put that as an OpenJDK project. So yeah, we've been working on it probably for about 18 months now. I lose track of time.
And as far as I know, there's also ideas to bring it to other operating systems. That's at least the last information that I got, that people looking into that too. So it's not only Linux in the future, it hopefully will also be available on Windows and Mac and whatever.
Yeah, because that's quite an important point, because the API and the implementation is decoupled from however we store the information underneath. So at the moment it's using CRIU, but it's not tied to that. Okay, I think we're probably kind of out of time. So thank you very much.